Hi, welcome back. We're going to go ahead and work some examples in this section, which is all about modeling with trigonometric functions. And what that really means is just using trigonometric functions to find real-world examples. So let's talk about the first example at hand. So we've got an airplane. And it needs to fly to an airfield. Let's see if I've got this one already. Hold on. Wait. Better. Okay. So we've got an airplane that needs to fly to an airfield that is located 300 miles east and 200 miles north of its current location. At what heading should the airplane fly? In other words, we're ignoring wind resistance and wind speed, and what we're asking is how many degrees north of east should the airplane fly? So think about creating a coordinate system, and your airplane's current location is right here at the origin. And where the airplane wants to go is an airfield out here. And we know some things. We know need to go that direction. And we know that this is 200 miles because the airfield is 200 miles north of my current position. And this is 300 miles. Now, what we need to figure out is what heading we need to set on our compass. In other words, what is that angle theta? You know how to do this. That's a right triangle. So we know that the tangent of that angle theta is equal to the length of the side opposite divided by the length of the side adjacent. So that means that theta is equal to the inverse tangent of 2/3. If we plug that into decimals, we find that our heading should be .588 radians, but here's the kicker. Our compass is not marked in radians, our compass is marked in degrees. So we want our answer to be in degrees. So 33.69 degrees. You need to tell the pilot which way you're going, and that is north of east. That's not so bad. All right, let's try another one. Okay, let's do a slightly more complicated problem. And this problem says that the hours of daylight in Seattle oscillate between a low of 8.5 hours in January to a high of 16 hours on July 4th. If you know that your garden is going to be happiest when there's 14 hours of daylight, in what month should we plant our garden? Okay. So let's think about how we're going to approach this. Let's talk about our months. So January, February, March, April, May. Now we're going to have to, June, July, August, September, and all the rest. We're going to have to put this on a coordinate system. So we need to decide what x is going to be in January. And this is where things get a little tricky because we think of January as the first month, but that's only because we don't have a 0 month. So we want x to be is 0, 1, 2, 3, 4, 5, 6, 7, 8. This is different than the month of the year. This is the x coordinate that we are using to represent these months. Okay, that's important to understand. So now let's make a sketch. Let's make a better sketch. Okay, actually, let's move that down. Right. So this is my x-axis. This is my y-axis. This is 0, 1, 2, 3, 4, 5. Now I only went out to 11. Why? Well, because remember that my months are off by 1. If I go to 12, that's going to be January again. So to make this clear, so this is January. This is February. This is March. April, May, June, July, August, September, October, November, December, and we'll get back to January. Now my y-axis is my hours of daylight. So in January, I have 8.5 hours of daylight. In July, I have 16 hours of daylight. In January, again, how many hours of daylight am I going to have? I'm going to back down to 8.5. So we see here that so the first thing I'm going to do is I have to write a function that represents the number of hours of daylight. And this is going to be a sinusoidal function. And we'll talk about all of the properties of that. The first thing we notice is my period is 12 months. So let me sketch this guy. I'm going to cheat a little. Okay. I do a better sketch when my scale's a little smaller. All right, so there we go. What does that look like? Well, it goes through the y-axis at a minimum, so it looks like a negative cosine. So we're going to say that my function, my y, my hours of daylight, is going to be a negative something times a cosine of something times x plus another something. And we usually say that this is a, and this is b, and this is c, or sometimes k. All right. We can get to b. Remember that my period is equal to 2 pi divided by b, which means that b is 2 pi over 12, which means that this is pi over 6. Now we can get to amplitude too, because amplitude is half of that distance. In other words, that is 2a. And that distance is so we want 16 minus 8.5, but I want to divide that by 2, and I get 3.75. So my amplitude is 1/2 of the max minus the min, or 3.75. Now we need to find our midline. Well, our midline is simply the average in between, or we can add 3.75 to our minimum. So my midline is going to be 8.5 plus my amplitude, which is 3.75. is 12.25. So the function that describes the hours of daylight over time in Seattle is negative 3.75 times the cosine of pi over 6 times x plus 12.25. Now, that's the first step. Second step is actually solve the question, solve the problem, answer the question. So what is the question? The question is, when are there first more than 14 hours of daylight? So if this is 14, I'm actually trying to find the coordinates of that point right there. So how do I do that? Well, I set y equal to 14. Okay, put Desmos away for a minute. All right, so we do a little work with that. I need to give myself a little more space. Bear with me for a second. There we go. Okay. So I'm trying to solve the equation. 14 equals negative 3.75 times the cosine of pi over 6x plus 12.25. Let's subtract our 12.25 from both sides. We get 1.75 equals negative 3.75 times the cosine of pi over 6x, which means that the cosine of pi over 6x equals negative negative 1.75 divided by 3.75, which means that pi over 6x equals the inverse cosine of negative 1.75 over 3.75. Let's see what that gives us. And we want this to be in radians. Let's make sure that we're in radians. We're going to take the inverse cosine of negative 1.75 divided by 3.75. And I get 2.056. That means pi over 6 times x equals 2.056. So let's take that number, that 2.0563 times 6 divided by pi, and I get x equals 3.93. Okay, so what month? Well, 3.93 means almost May. So it's right here. So you would plant in late April. All right. I'm going to stop here and I'm going to come back in the next video with a slightly more complicated example.